Gravitational waves are ripples in the fabric of spacetime. First predicted by Albert Einstein as part of his general theory of relativity in 1915. These waves, traveling at the speed of light, are generated by some of the most energetic and violent processes in the universe. They carry information about their origins and the nature of gravity itself, providing a new way of observing and understanding the cosmos. In this overview, we will explore the fundamental concepts behind gravitational waves, their detection, the science surrounding them, and their significance in modern astrophysics. We will delve into the theoretical foundation laid by Einstein, the observational breakthroughs that have followed, and the potential for future discoveries in gravitational wave astronomy. Einstein's general theory of relativity, published in 1915, revolutionized our understanding of gravity. Rather than describing gravity as a force between masses, as Newton had done, Einstein proposed that gravity is a manifestation of the curvature of space-time caused by mass and energy. This conceptualization led to a completely new way of thinking about the fabric of the universe. In general relativity, masses cause the curvature of space-time, and when massive objects accelerate, they can produce disturbances that propagate outward, like ripples on the surface of a pond. These ripples are gravitational waves. Einstein predicted that if large masses accelerate rapidly enough, they could generate detectable gravitational waves. Gravitational waves are fundamentally different from other types of waves in the universe, such as electromagnetic waves. These waves stretch and compress the fabric of space-time itself, causing distances between points in space to fluctuate. The wavelength of gravitational waves depends on the frequency of the source, and their amplitude diminishes with distance from the source. The most well-known sources of gravitational waves are binary systems, where two massive compact objects, such as black holes or neutron stars, orbit one another. As they move in tight orbits, they emit gravitational waves that grow stronger as the objects spiral in toward each other. When these objects merge, they release a tremendous amount of energy in the form of gravitational waves. Another possible source of gravitational waves is a supernova, a massive star's violent explosion at the end of its life. The asymmetry in the explosion can create gravitational waves, although the strength of the waves from this source is much weaker than those from binary mergers. When two neutron stars collide, they create a cataclysmic event, often associated with gamma-ray bursts and heavy element formation. These events also produce gravitational waves. Observing such events provides scientists with valuable information about the equation of state of neutron stars and the fundamental nature of matter under extreme conditions. Gravitational waves might also be produced in the very early universe during the epoch of inflation, a rapid expansion of space that occurred within the first fractions of a second after the Big Bang. These primordial gravitational waves carry valuable information about the conditions of the universe in its earliest moments. One of the greatest challenges in detecting gravitational waves is their incredibly weak interaction with matter. The distortions they cause are minuscule, typically on the order of a fraction of the diameter of a proton, making detection extremely difficult. The precise instruments required to detect these waves must be incredibly sensitive to minute changes in distance. LIGO is the first and most famous detector designed to detect gravitational waves. It uses two large perpendicular interferometers located in Hanford, Washington, and Livingston, Louisiana. When a gravitational wave passes through Earth, it slightly alters the distance between two mirrors in the interferometer arms, which can be measured as a phase shift in the light reflected from the mirrors. The first successful detection of gravitational waves in 2015 was made possible by LIGO. In addition to LIGO, the Virgo detector in Italy and the Kagra detector in Japan have also contributed to the detection of gravitational waves. These detectors work in a similar manner to LIGO, providing triangulation for more accurate measurements and improving sensitivity to a broader range of gravitational wave frequencies. The future of gravitational wave astronomy looks promising, with the development of next-generation detectors like the LISA, which will be placed in space to detect lower-frequency gravitational waves. These detectors will be able to study sources that are too distant for ground-based detectors to observe, opening up new frontiers in our understanding of the universe. On September 14, 2015, LIGO made the historic first detection of gravitational waves from a binary black hole merger. This discovery confirmed Einstein's century-old prediction and marked the beginning of a new era in astronomy. The detected signal, known as GW150914, was a powerful event that created a ripple in spacetime and provided direct evidence of black holes colliding. The detection of gravitational waves from black hole mergers provided not only confirmation of the existence of gravitational waves, but also new insights into the behavior of black holes, their masses, spins, and the way they interact. It demonstrated that gravitational waves could be used to study black holes and other astrophysical objects in ways that were previously impossible with traditional electromagnetic observations. The breakthrough discovery of gravitational waves earned the 2017 Nobel Prize in Physics. The prize was awarded to Rainer Weiss, Barry C. Barish, and Kip Thorne for their contributions to the LIGO detector and the observation of gravitational waves. This recognition further solidified the importance of gravitational wave astronomy. Gravitational waves offer a unique opportunity to study binary black hole systems. By analyzing the characteristics of the waves, scientists can infer the properties of the black holes involved, including their masses, spins, and orbital parameters. Gravitational wave observations have already revealed black holes with masses that were previously thought to be impossible. The detection of gravitational waves from neutron star mergers has opened the field of multi-messenger astronomy, where gravitational wave signals are combined with electromagnetic signals such as gamma rays, X-rays, and optical light. This collaboration has led to groundbreaking discoveries, such as the observation of kilonovae and the identification of heavy elements like gold being created in these collisions. Gravitational wave astronomy provides an important test for Einstein's theory of general relativity in the strong field regime. While general relativity has been confirmed in weaker gravitational fields, gravitational waves offer the chance to study gravity under extreme conditions, such as in the vicinity of black holes, neutron stars, and during the Big Bang. Any deviations from general relativity could provide clues to new physics. Gravitational waves hold the potential to unlock secrets about the dark components of the universe, including dark matter and dark energy. For example, gravitational waves from the early universe could provide crucial information about the nature of inflation and the existence of primordial gravitational waves, which could inform theories of the universe's early moments. Gravitational waves also provide a powerful tool for cosmology. By studying the waves from distant sources, scientists can measure the expansion rate of the universe, study the properties of the intergalactic medium, and probe the structure of spacetime itself. These measurements could provide answers to some of the most fundamental questions in physics. The field of gravitational wave astronomy continues to evolve. As more detectors are built and more events are observed, the scientific community expects to learn more about the formation and evolution of black holes, neutron stars, and other compact objects. New physics, such as theories of quantum gravity or modifications to general relativity, could emerge from these observations, potentially revolutionizing our understanding of the universe. Gravitational waves have opened up an entirely new window on the universe, enabling us to observe phenomena that were previously invisible to traditional telescopes. Since their first detection in 2015, gravitational waves have already provided profound insights into the most extreme processes in the universe, from black hole mergers to neutron star collisions. As detectors improve and new instruments come online, the future of gravitational wave astronomy holds immense promise, offering the potential to answer fundamental questions about the nature of gravity, space-time, and the cosmos itself.